We repeat our common theme, electron-rich atoms will always move to electron-poor. Negative charge or slightly negative charge, a lone pair, double, triple bond will always go towards a place that is missing an electron entirely or is slightly positive, or in some cases, if you have an unpaired electron or free radical, that's also electron-poor. We start our Grignard synthesis with our alkyl halide to actually make our Grignard reagent. What that's going to do is that's going to put a negative charge on a carbon. We're making a carbon nucleophile. That's really the sole purpose of a Grignard, is to create a carbon nucleophile. Carbon's a pretty stable atom. It's in group 4 on the periodic table, so it neither wants to gain or lose electrons too much. It's not too comfy with that negative charge. What we're going to do is we're going to extend the alkyl chain length and make an alcohol by adding it to electron-poor carbon. So just to review the periodic table, carbon's in group 4. It's not very energetically favorable for it to gain or lose 4 electrons to resemble noble gas, so it's not as reactive as your group 1s or your group 7s, where only one movement, or I should say movement of 1 electron is required to resemble noble gas. So again, the Grignard reagent was really a breakthrough to create that carbon nucleophile. And what we're going to do is we're going to connect it with the very common carbonyl carbon, which is delta plus. It's electron poor. You see carbonyls everywhere in nature because it makes that carbon reactive. So our electron-rich carbon nucleophile is going to attack our electron-poor carbonyl carbon in this aldehyde here. This 3-carbon aldehyde, that's propanal. So that's going to attack there. It's going to push the electron. It's going to break the double bond, push the electrons up to get an O minus. And then once you're past that first step, the second step is really just to protonate that negative charge. You're going to add water separate. So you have first the nucleophilic attack, the carbonyl carbon, and then proton transfer, where the O minus is going to take that delta plus, or that proton, from water. So water acts as a weak acid in this case. I drew the different carbons from different molecules in white and yellow. Hopefully that will help you to keep track of it. And again, water's behaving as an acid in this case. Acid's always a proton donor. If you're doing some bookkeeping, there are side products there. I always like to double check to be sure that I have a nice balanced molecule or side product. Mg is not a transition metal, it's always +2. And you see Mg on top being +1, although remember that it's actually kind of +2 because bromine's going to be -1, but that's not that important. You have to keep water away from a Grignard reagent because it's so reactive. It will grab a proton from anywhere, particularly water, which behaves as a weak acid or proton donor. You have to save water to the second step, so you have to write that as step 2. So by popular, in nature, carbonyl carbons are everywhere. It makes carbon more reactive. And of course, now you can see why Grignard won the Nobel Prize. Having a negative or electron-rich carbon is pretty rare. So I have my Grignard reagent here, and I'm just doing a little bit of bookkeeping for my charges. And carbon nucleophile will attack the carbonyl carbon. And once you connect that alkyl chain, if you count the number of carbons you have, hopefully from there you're home free. All you got to do is protonate that O minus in the second step. Final product is going to be, in this case, a tertiary alcohol. So a ketone plus a Grignard reagent, we have a tertiary alcohol. If we have an aldehyde, it's going to be a secondary alcohol, as we had earlier. And just keeping track of my charges here, you have Mg. It's actually prefers to be +2, but in most books you'll just see it as written as a +1 to counter ion to your carbon nucleophile. What if a carbon nucleophile attacks an epoxide? Well, you can see that the electronegative oxygen is pulling electron density away from those 2 carbons in that triangle shape, making them delta plus. The carbon nucleophile will attack the least sterically hindered carbon, just because it's easier, it's energetically favorable to do so. And it's going to break that bond and push the oxygen off to create an O-. So it's essentially the same reaction. As long as you're keeping track of where your carbons are, you should be in pretty good shape. The second step is the same. You're going to protonate that O- and it's electron rich, moving to a slightly electron poor hydrogen to get your alcohol. So again, the epoxide is a very similar reaction, and keeping track of your side products, you have Mg, OH, and Br. In this case, you produce a secondary alcohol product. So that's pretty much it. Those are your reactions of Grignard reagents with aldehydes, ketones, and epoxides. So in summary, we're following our electron-rich atom to electron-poor atom pattern. That's really the way the whole universe, Mother Nature works. If you can understand that path of electrons going to places where they're needed, you pretty much get 99% of all reactions. In this case, we see electron-poor carbonyl carbons everywhere. They're in aldehydes, ketones. We have them in epoxides, carboxylic acids, esters, amides, amino acids. However, that carbon nucleophile is pretty rare. So if you want to connect two carbons together, you got to have an electron-rich carbon. And again, that's why Grignard, or the Grignard reagent, was such a breakthrough, and why Grignard won the Nobel Prize. It's a pretty dope reaction. So good luck. Peace.